welcome to the existence and uniqueness theorem for nonlinear equations. Again, just focusing on first order. So recall we have already seen an existence and uniqueness theorem for linear first order equations. So if we have the IVP, initial value problem, y prime plus p of xy is equal to g of x with the initial condition y of x naught is equal to y naught. Then we had if p of x and g of x are continuous on the open interval AB containing x naught, then there exists a unique solution to the IVP on the interval AB. So in this condition, as long as we have that continuity for both P and G over the interval, there is a unique solution on that entire open interval. Nonlinear, this is a little different. So for nonlinear equations, again, let's consider the IVP y prime is equal to f of x comma y, and y of x naught is equal to y naught. We are going to break this into two pieces. We are going to have a theorem, conditions for existence, and then conditions for uniqueness. So for existence, if f is continuous, over an open interval, or sorry, not interval, rectangle. So it's continuous over the open rectangle R. Which we'll define as A is less than X is less than B, with Y is less, sorry, not Y. C is less than Y is less than D. Containing the point x naught, y naught, then there exists a solution to the IVP on some open interval contained in AB. So essentially what we have here, we have our XY plane. Because f is a function of both x and y, it only makes sense to talk about continuity on a two-dimensional region. So let's say here's our two-dimensional region. So we're going from A to B in x coordinates and from C to D in y coordinates. And then x naught, y naught is somewhere in the middle. So our point x naught, y naught is somewhere in that rectangle. Let me update my screen briefly. Sorry about that. So here I've just drawn an open rectangle, meaning we don't include the sides. X runs from A to B, Y runs from C to D, and then I've picked out a point which will be our x naught, y naught contained within that rectangle. So we have R is this entire rectangle. So we have an open rectangle R. We have our point AB. And what we're saying is that there is some interval contained within AB, also containing x naught, which will be our solution, where our solution is defined. So we have some open interval contained in AB. I should specify that this is containing x naught. And so we have a solution. It's not on that entire AB, but we do have an open interval on which it's defined. So at this point, we've found the conditions for having a solution, but we do not yet have the conditions for uniqueness. So next up is uniqueness. So for uniqueness, we are not only going to look at continuity of f, but we are going to look at the continuity of its partial derivative with respect to y. So if f and the first partial of f with respect to y are continuous, on open rectangle R, which will be A less than X less than B, and C less than Y less than D, containing the point X naught, Y naught. Okay, so far these are the same, the F continuity guarantees our existence conditions are met. So if F and the first partial with respect to y are continuous on this open rectangle R containing x naught, y naught, then the solution, or there is a unique solution to the IVP on some open interval contained in AB, which contains our initial point x naught, y naught. So again, existence, we just need the continuity of F over this open rectangle. Uniqueness, we also need continuity of that first partial with respect to y. So in the next video, we will go ahead and do a few examples and find where we have our solution and where we have our unique solution.